Okay, so the last task you were asked to do for topic one, system architecture, was to go through the what things have I understood and highlight to me what things you did and you didn't understand. I've kind of looked at those, and there were a few things that have come up a couple of times. So I intend to go over those. I'm actually going to go through really quickly through all of them, but I'll focus a little bit on the topics that people said they were struggling with. Okay, so system architecture recap. I can explain the purpose and function of the CPU. I don't think anyone picked this one up. We know the CPU is the brains of the system. It executes our programs. I can describe the fetch execute cycle. Certainly done. So fetch execute cycle. What is the fetch execute cycle? Let's go look. I'm going to use the slides, the answers to the slides that you were using in the previous lesson. And here we go. Stage one: fetch the instructions. What does it mean by instructions? Where does it fetch them from? Well, a computer program is made up of instructions that the CPU carries out. These are copied across into the main memory, and that's where they'll fetch from. We use the register called the program counter to point to the address of the next instruction we need to fetch. After that, we decode that instruction and we work out what is it we need to do. Do we need to add some numbers? Are we comparing two values? And then the control unit will set the rest of the CPU up in order to be able to execute that instruction. They use different parts of the CPU depending on what the instruction is. Okay, so I can explain what the arithmetic logic unit, okay, the ALU, it's a main part inside of the CPU here, and as its name suggests, it performs arithmetic and logic functions. So if we had to add two numbers together, this is where it would take place. We'll look later on in the course at something called logic gates, and we'll see how this really actually kind of happens at a low level in binary. It also performs logic operations, the ands and ors and nots that are included in our program. That's the ALU. I can explain what the control unit is. I think I just did that a minute ago. The control unit is a part of the CPU that once we've decoded an instruction and we know the system knows what it needs to do, it will set things up. So for example, it would kind of set up the ALU to perform an add instruction, or perhaps it will, if we're going to store something, it will put an address onto the memory address register. So it's kind of like at the heart, the controlling part of the CPU that sets everything else up. Okay, so we've got that one and that one. I can explain what cache is. Okay, cache is a type of memory. It is the memory that is on board the CPU, and it is a very fast memory, but it's also quite small. And the purpose of it is to hold instructions that might be repeated. So for example, if you're going around a loop if your program has a loop inside of it, the same instructions will be executed several times. It takes time to go and fetch these instructions from memory. Therefore, the cache, if it has a copy of those instructions already, can receive those, read those instructions much quicker from cache than we could from main memory. And what is meant by the term a register? Well, there's lots of different registers inside of a CPU. Most of them are special purpose. Some have a general kind of purpose. But essentially what a register is, it is another piece of storage, but for a specific kind of function. So for example, we've mentioned a program counter. This is a register that holds the address of the next instruction to be fetched from the main memory. I can explain what the memory address register and the data register for in the von Neumann architecture. Okay, the von Neumann architecture is essentially the bit that kind of says here we are kind of getting our instructions and data from main memory. We are as the fetch, and then we're decoding and executing. So it's this idea that the instructions and data come from main memory. In order to do that, you need to know two things. Okay, you would need to know where in memory the instructions are, so that's the memory address register, and then you would need a place of holding the instructions and the data that are perhaps associated with them inside of the CPU, and this is the job of the memory data register. I can explain what the program counter is used for. Done that a couple of times. Say it again though. It holds the address of the next instruction to be fetched from memory. What is the accumulator used for? Okay, well, the accumulator is another register inside of the CPU, and effectively it holds the results of operations performed by the ALU. So if we had an instruction that was to add two numbers together, the ALU will add them together and it will put the result into the accumulator. So the accumulator is a special register that holds the values of calculations or logical expressions. If maybe you're comparing two things, it will tell us if they're the same or not. Explain how the clock speed affects the CPU performance. So if we think of all of these steps that are going on in the von Neumann architecture, and fetching and decoding and executing and putting things in registers, all of these have to happen in an order and in at specific times. So the rest of the system understands where it is in the system. So we have something called a clock. And effectively a clock is a square kind of wave, electrical wave, that repeats itself. On each kind of edge of the clock, the next part of the fetch, decode, execute cycle will be performed. Therefore, if you think of this as a little bit like maybe a marching band, if you kind of have them marching really quickly, 1, 2, 3, 4, 5 steps at a time, they're going to get from one place to the next a lot quicker than if they're doing a slow kind of march of 1, 2. Well, the clock's the same. Okay, if we in the same period of time, if we have lots of clock pulses, and if we think each one of these is perhaps a fetch, a decode, etc., here we're getting through them a lot quicker than we are with a lower clock speed. It's measured in hertz, and that tells us how many times the clock pulse will repeat itself in 1 second. So how many times it will perhaps go from here to here in 1 second. What's next? So we've got... I can explain how the size of the cache affects the CPU performance. Well, we said earlier that the cache holds instructions that might be needed again if they are repeated. Well, the more information we can hold in the cache means that there is less need to go back to the main memory. If we can only hold a few instructions in there, we'll perhaps repeat those, but then we'd need to go get the other newer instructions from main memory. So having the larger cache means that we won't have to keep going back to the memory so often. I can explain how the number of cores affects the CPU performance. Okay, in this case here, if we think about the CPU as being one chip, and it has all of the different parts inside of it that we've kind of looked at down here, one way is we could kind of say, well, let's put 4 of those, perhaps, quad core, into one computer. And therefore, in theory, we could kind of be doing 4 things at once, and therefore would effectively speed up the processing performance of the computer by 4. I can explain the purpose of embedded systems. Well, an embedded system is one that has is a larger system that has a computer system built within it. Often these are really different to perhaps our what we think of as a computer, like a desktop or a laptop or a tablet or something. They are the small computers that are embedded in things like cars and washing machines. If we think about it, a washing machine, it has buttons on the front, they're inputs. We can choose different cycles for it to different washes for it to do. There needs to be a program, and there needs to be a CPU that works out what it's going to do depending on the cycle that you've kind of chosen. There are outputs because it needs to turn motors on and off and open and close valves. Therefore, we can say a washing machine is an embedded system. It has a computer embedded within inside it. And we've done the giving examples there. Okay, there you go. That was a really quick kind of run through of section 1.1, system architecture.